Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. And in this module we are trying to understand how does the operating system manage the CPU by providing this abstraction of a process, right? And within the second module we are currently on the third topic, that is system calls, exceptions and interrupts. And within this topic, we are trying to understand the different mechanisms that exist in the computer system so that the user process and the operating system can communicate with each other. So currently, we are discussing the system calls, and we have spent a fair amount of time understanding what is a system call, why do we need it, how is it implemented, right? So now in this video, I am going to summarize everything that we have learned about system calls by explaining you a detailed flow of what are the sequence of events that happen when a system call is made. Right from the starting till the beginning, we'll go over the detailed steps of all the events that occur during a system call. So without further ado, let's get started. So let me start the discussion with this diagram. We have already seen this diagram multiple times. Let me quickly recall what it is trying to show. So in this diagram, as you can see, there are two parts. The red part is when the code is being executed in the kernel, and the blue part is when we are executing in the user process, right? So all of these red arrows means that we are executing kernel code, right? This is the kernel region, and all of these blue arrows mean that we are executing user process. So basically, as we go from left to right, the code execution is moving further, the time is increasing. This is basically a rough description of the execution of a user process, the timeline of a user process, right? Here you can see the user process is created by the kernel, and there is some execution that happens, and in the end, when the user process is done, it requests the kernel to terminate the process. So let's focus on what is happening in between. So when the operating system launches the process, the control is shifted to the user process, right? And as you can see, we have talked about this in the previous video, that this is the return from trap instruction, which is used to transfer the control from the kernel to the user process, right? And drop the privilege level from kernel mode to user mode. So whenever we are executing user process, we are executing in user mode, right? This blue region. And whenever we are executing kernel code, we are in the kernel mode, this red region. So when the user process is executing, as you can see, it makes system calls, right? During its lifetime, it frequently makes system calls. In this timeline, it makes two system calls, right? In fact, three system calls. So the first one is the read system call, right? This is just an example. The second one is the mmap, and finally, it also makes a system call to terminate the process. I have not shown it here, but as you can see, the point of this diagram is to show that how the user process, the execution of user process alternates between executing kernel code, then user code, and so on. This alternation keeps on happening when until finally the user process requests the operating system to terminate itself, right? So now what we are going to do in this video, we are going to zoom into one of these system calls. Basically, we want to take a closer look at what are the events or the steps that happen when a system call is made, right? So let's look at the system call in more detail. So this is how the timeline of a system call looks like. So let us go over the different parts of this diagram. So now we have three parts in this diagram. The red region, like before, is the kernel, right? This is the part where we are executing in the operating system, right? These red arrows. And this blue region is basically the user space. And within the user space also, there are two distinctions I have made. The light blue color that you see, it is when we are executing the user application code, right? And this darker blue that you see, this region is within the programming library. In this case, I have taken the example of libc, right? So this is where we are executing inside the library, and as we saw in the previous video also, how the library is involved while making a system call. So basically, we want to summarize all of the steps that happen when we make a system call. So let us start. So as you can see, I have listed here 9 different steps, and there is a step 0 also. So we'll start with step 1 and see what is happening in the system call. So let us start with the first step. I will talk about step 0 later on. So let me start with the step 1. So let us assume that we are executing a user application, and within the user application, there is a statement where we are making a system call. We are invoking a system call. So here, let's say we are invoking the read system call, right? And this is the statement that is part of the user process. Okay, so here we are, I'm talking about this point, right? We started here. The user process is executing its instruction, and at some point it encounters a statement where it is making a system call. Okay, so as you can see, the read this function that you see is just a wrapper over the system call which enters into the C library. This is not the actual system call. We have discussed this in the previous video in great detail. This statement that you see, right, when you're writing your code, when you're writing your that system call statement, what you are writing is actually just a wrapper. It is not the actual system call. It is a wrapper over the system call. And what does that wrapper do? When that wrapper, it basically takes you inside the C library. Okay, so as you can see, this arrow going downwards. So when this statement is executed, we enter the C library. Okay, now let's go and see what is happening in the second step. Okay, so now we are executing inside the C library. Okay, this is the library code. So what the library does, so as we saw in the previous video that the C library reaches a macro, right? Within that macro, there is some assembly code. And in that assembly code, we are basically invoking the system call. And as part of that assembly code, that small assembly code, there are a few things that happen. And one of the things is that the C library places the parameters or arguments in its right place, right? So the C library has to follow the convention that is established by the operating system and the hardware when making a system call. So we have discussed about this in the previous video in great detail that a system call requires hardware support, right? It requires the trap instruction. So when we are making a system call, basically the trap instruction that we are going to execute, that is very specific to the hardware platform that you are executing upon. So when I say hardware platform, I mean the instruction set architecture, whether you are on x86 or you are on ARM architecture or you are on RISC-V architecture. Depending on the hardware architecture, the CPU architecture you are on, the trap instruction will be different, and even the registers would be different. So the point that I want to convey is that the actual invocation of the system call, that piece of assembly code, is very specific to a particular hardware, obviously also the operating system. So the C library has to follow the convention, agreed upon convention, or you can say the protocol established between the library and the operating system and hardware. Okay, so as part of the as part of the assembly code, as I said, one of the things that the library has to do is that it has to place the arguments in certain registers. So as part of the architecture, the convention that the architecture establishes is that it expects the arguments of system calls to be in certain registers, and those registers vary from one platform to another. So this library has to place those arguments in certain registers, and if the arguments do not fit in the registers, then they have to be placed in the memory or on the stack, right? Sometimes the number of arguments or the size of arguments could be large and they need to be placed in the memory. So this was the second step. Then what happens as part of the assembly code is the trap instruction. So let's go to the third step. So this is the third step, this red glowing arrow, right? This is the third step. Oh, I missed one. So basically another thing is that when you're pushing the parameters, the library also places the system call number corresponding to that particular system call, right? So basically not only the C library places the arguments, it also places a unique number which is related to that particular system call, right? So the idea is that when you're making a normal function call, let's not talk about the system call, let's talk about a normal function call. So how do you make that function call? While making the function call, there is a jump statement to a particular address, and that address is the starting location of the function, right? But instead, when you're making a system call, you're not allowed to specify a address, because if the user process is allowed to specify a random address in the kernel code, then the user process is basically having the liberty to execute any piece of kernel code, right? So we do not want the user process to have this liberty. So as a safety mechanism, the user process is not allowed to give any address while making a system call. When we are making a system call, we just specify a number. The number is corresponding to that system call. So the read system call will have a unique number, and for all the system calls in the operating system, there will be a unique number. So what the operating system does is that it takes that number and indexes into a table. It maintains a table of all the system calls that are there in the that it supports, and in that table, using that number, it can get the address of the routine of the system call routine from where it has to start the execution, right? So instead of specifying the address, the library places the system call number, which will be used by the operating system to find the address, right? So this indirection is a protection mechanism. Okay, so now let's go to the next step. So the next step is the this third step, right? So as part of the second step, we were pushing the parameters and the system call number. Now in the third step, in that assembly code only within the library, there is the trap instruction, right? So here you can see, I'm assuming we are on the x86 architecture. On the x86, the trap instruction is named syscall, and the return from trap instruction is called sret. Okay, so this is the part where the trap instruction is being executed. And as I said, there are two functions of the trap instruction. The first is to raise the privilege level. So as you can see, we are moving from the blue region to the red region, right? So this is the region where the code is executing in user mode, right? And the red region is the area where we are executing in kernel mode. So as part of the trap instruction, the privilege level is raised in the hardware, and the control is given to the operating system. So let's look at the next step. So before moving on to the next step, let's also look at how the trap instruction accomplishes what we just said, right? Like transferring the control and switching the kernel mode. So in order to transfer the control, it saves the program counter into a special register that is called EPC, that is exception program counter. So basically, wherever it was executing, that program counter, it saves into a particular register that will be restored when we are returning, right? We have to start the resume the execution exactly from the point, right? So when we will return, then we will restore that register. So we are saving it to a particular place so that we can restore it at a later point in time. And the next thing it does is it raises the privilege level by setting the privilege bit in the CPU, right? We have talked about the privilege mode bit in the CPU. So there is a bit in the program status word, and it indicates the current privilege level. So as part of the trap instruction, the bit is changed, the bit is flipped. So basically, you can see when you execute an instruction, there are certain micro steps that happen, right? Basically, one instruction has certain micro steps. So as we saw, the first micro step was to save the program counter. The second micro step was to flip the register, the privilege bit, right, in the register. And then the third micro step you can think of as that jumping to a well-defined location. So now we have saved the program counter, right? And then we will change the program counter. So the new value of the program counter will be inside the kernel code. So what we just did is that we were executing inside the C library. We saved that program counter and we swapped it with a new program counter, which was a well-defined address inside the kernel. This is how the transition from the user process to the kernel takes place, all happening in one instruction, right? This is the syscall instruction, and all of these micro steps, that is saving the program counter, flipping the privilege bit, and replacing the program counter with a new value, all of that happen in the syscall instruction, right? So we know that when the syscall instruction is being executed, what happens is that a new value of basically a new address is placed in the program counter. As you can see, this is saying that when the syscall instruction will be executed, the execution will be started at a predefined location in the kernel. So let's talk a bit about this predefined location. So what is the address that the syscall instruction should put into the program counter, right? So we know that the user process is not allowed to pass any address, right? It can only pass the system call number. So there is a safety mechanism, and it is only allowed to pass the system call number. So now the question is that if the user process is not specifying any address, so where should the kernel start executing when this syscall instruction executes, right? So this is basically defined by the operating system only. So when we say there is a predefined location, this location is defined by the operating system, right? So let's talk about this step 0. right? So what happens is that when the computer is booting up, at that time, what the operating system does is that it knows that when the user processes start executing, then there will be system calls. They will invoke system calls, and every time a system call is made, the control has to be transferred to the operating system. So what the operating system does is that it programs the address from which the execution of operating system should start whenever a system call is made, and this happens during the boot time. So within a well-defined memory location, the operating system registers it. So when we say registered trap, so a system call is a trap. So we'll study about other types of traps like the exceptions and the interrupts, right? This whole topic, that is system calls, exception, and interrupts, all of these are different types of traps. And whenever there is a trap, basically we trap into the kernel. The control is transferred to the kernel, right? And the system call, as I said, is one type of trap. So for every type of trap, when the control is being transferred to the operating system, we want to specify from exactly where should the kernel start executing, right? So whenever there is a system call, then there is a well defined memory location, that basically I'm saying that is the address of the instruction from which the kernel should start executing, right? And that address is placed in a well defined memory location. And when the syscall happens, when the syscall instruction is executed, that predefined value is used as the new program counter, right? So let me repeat what I just said. At the boot time, what the kernel does is that it, in a well-defined memory location, it puts a address. And what is that address? That address is the address of the instruction from which the kernel should start executing whenever the system call is made, right? So whenever the user process makes the system call and this trap instruction is executed, the trap instruction will use that address placed in the well-defined memory location by the operating system during boot time, so that the further execution can start from that particular address, right? This is a very important step, that is registering the trap at the boot time. So you can see this operation should be only done by the operating system, because we are defining the address from which the kernel will start executing. So this is something which is sensitive and has to be done by the kernel only, this because we can only trust the kernel. So at the boot time, it registers all the different types of traps that can occur, and whenever such a trap occurs, from which address should the further execution happen. Basically, it is defining the entry point into the kernel. Once the entry point has been defined during the boot time, whenever a trap occurs, for example, whenever a system call occurs, and that instruction will place the address of the entry point, and then from there onwards, the kernel will start executing. So now let us talk about the step number 4. Now we have entered into the kernel. Okay, so let's see what is the first thing that the kernel does. So the first thing that the kernel does is that it has to save registers like the stack pointer and the general purpose registers onto the kernel stack. So let's see what is happening here. So if you observe carefully, the user process was executing, and suddenly the trap instruction, in this case the syscall instruction, was executed, and suddenly the control has been transferred to the operating system. So we have only stored the program counter of the user process. Rest of the registers that were associated with the user process, like the stack pointer, the general purpose registers, all of them are still in the context of the user process, right? So we have talked about the stack pointer and how when we are executing the code, the stack is heavily used, right? We have talked about this in the process address space topic, right? So the stack pointer still points to the user stack, and in the general purpose registers is where the all the computation happens, right? So the temporary values that were calculated as part of the execution of user process, they're all still there, right? The context, we were still executing in the context of the user process, right? So all of these values have to be stored somewhere, because when we resume the user process, we will require all of these values. So what the operating system does before going on to the system call, it has to first of all save all of these important pieces of information, right? It has to save the stack pointer, the general purpose registers. All of this are associated with the execution of the user process. The execution of the user process suddenly transition into the kernel. So all of these important values have to be stored somewhere. And where are they stored? They are stored on the kernel stack. So just like the user process, the kernel also as a stack, right? When we are executing, we execute on the stack. So when the kernel executes, it also has a stack, and not just one. There are many stacks associated with the kernel. We'll talk about the kernel stack in the last video of this topic, that is when we discuss traps. But the point that you should understand is that when the kernel starts executing, it has to save the pieces of information which are still associated with the user process, and these pieces of information will be used when we are returning to the user process, when we are resuming the execution, right? All of this is part of handling the trap. Another thing that the kernel does when it handles the trap, it determines the cause of the trap. So let me repeat once again, what is a trap? So these events like the system calls, exceptions, or interrupts, these are special events, and when they occur, basically they need the immediate attention of the operating system. So whenever a system call is made, it basically means that the user process requires certain service from the operating system. We haven't yet talked about exceptions or interrupts, but in brief, I can say that exceptions are basically fatal errors, which when occur, then the operating system has to do certain error handling, right? Whenever a user process or some fatal error has occurred in the system, the kernel has to deal with that. And as I said, these are events which need the immediate attention of the kernel. Similarly, if you talk about interrupt, it is when the IO devices or the hardware devices need attention from the kernel. So, right, all of these events which we call traps. So basically, these are different types of traps, and the common thing is that whenever such a event happens, we have to transition into the kernel and do something, right? We are trapping into the kernel from wherever the execution was happening. We have to go right into the kernel. You have to trap right away into the kernel to immediately deal with the situation, right? It could be a system call, it could be an exception or an interrupt. So as before going on to like the operation that the kernel has to do depends on the kind of trap it was. In this case, this was a system call, right? So the operating system has to determine what caused this trap, whether it was a system call or whether it was an exception or whether it was an interrupt. Depending on the trap, it has to handle it in a different way. When there is a system call, then it has to call appropriate system call routine. If there is a exception, then it has to determine what was the error, and depending on the error, it has to invoke appropriate error handling routines. In a similar way, when there are interrupts, there could be interrupts from different types of devices, and each of the devices have their own handler routine. So here basically we have to determine which routine would be executed by the kernel. So the kernel in this step, before going forward, has to carefully determine why this trap was caused and what we should do. Now let us come to the most important step, that is step 5. In this step, we are actually going to execute the system call. So let us assume that the system call routine for the read system call is named as sys_read inside the kernel. So I'm assuming a name for the exact function that will be executed inside the kernel code. Let's just say the name is sys_read. So what does the kernel do? Right, the first of all, the kernel basically, it only has the system call number, right? So it has to determine what is the address of sys_read, right? Remember what we did during this second step, when the library was pushing the parameters, instead of passing an address, it just gave a system call number. And using that system call number, now the operating system has to find the exact address where sys_read is located. So it will have a table, and depending on the number, it will index into the table and get the exact address where the routine is located, and then it will jump to that routine, right? The appropriate kernel routine is called using the system call number. Then what happens? Then the kernel verifies whether the parameters that were supplied by the user process, they are valid or not, right? It has to basically determine, is there anything malicious in the arguments, right? So what I mean to say is that there are different ways in which the user process can do malicious things, and in the kernel, we only trust the kernel, right? So the kernel has to be very cautious of what it is doing. So as part of a safety mechanism, all the arguments are properly verified, right? For every system call, for every type of argument, they are properly verified by the kernel, so that something wrong does not occur, right? So this safety check happens because now whatever kernel does, it has to do it correctly. Then after verifying the parameters, the actual operation is performed, right? Perform the operation that was requested by the system call routine. In this case, whatever file was given, whatever buffer was given, so that operation will happen. We will read some bytes from the file, and then we'll return that data into the buffer, right? So that actual operation has been performed. Then finally, during that operation, what can happen is that the process might block and we might want to switch to some other process. What does this mean? Right, for example, let's say we make a system call, and in that system call an IO operation has been initiated, or for some reason we have to wait for some event, right? So let's say in this operation, some IO operation was initiated. When we say we want to read, let's say we want to read from a hard disk. Okay, so when we want to read from hard disk, it will take a certain amount of time till the data is available. In the meantime, what we can do, instead of waiting here, we can switch to some other process, right? So whenever we make a system call, there is a chance that we might want to switch to some other process. Or another example is that, let's say this was the terminate system call. This was a system call which the user process had made to terminate itself. So right here, the process execution will stop and we will need to execute some other process. It could be also a system call where the user process has explicitly asked to wait, right? So there are many cases basically in which what we want to do, what we might want to do is that we want to pause the execution here for some time for this user process, and when we return to some other user process, right? And later on, when the when the event for which we were waiting has happened, then we can resume this process. So this might not happen every time. Only in some cases we might want to wait, right? And what will happen in that, here the kernel will switch to some other process. So basically it will enter from one process and exit into another process. So if there has to be a process switch, then this is the place where it happens, right? So finally this step is done. Then we start returning. So now let's come to the sixth step, that is prepare for return. So whatever we'll do now will be in a way a reverse of whatever we did while entering here, right? 1 2 3 4 5, whatever we did there, now we are going to do things in reverse. So remember what we had done during step 4. We had saved the stack pointer and the general purpose registers on the kernel stack to save the context of user process execution. So now when we are preparing for return, we will do the opposite. We will just restore those values. So we will restore the stack pointer so that it points to the user stack. We will restore the general purpose registers so that when the user process resumes execution, it can get those values, right? It can start executing right where it had left off. So when we entered the kernel, we saved all of the information that was related in context to the user process. Now we are restoring those important pieces of context so that the user process can start executing right where it had left off. So this was sixth step. Then there is the seventh step. So what is this? Execute return from trap instruction. Okay, so in the x86 architecture, it is SRET. So the trap instruction in x86 is syscall, and the return from trap is called SRET. Okay, so now again, as I said, as part of this instruction, certain micro steps will happen, and it will be the reverse of what we did when we entered the kernel. So what we did when we entered the kernel, we saved the program counter, we switched the kernel from user mode to kernel mode and started executing inside the kernel. So now we will do the reverse of those things. So let's see what are the things that we will do as part of the return from trap instruction. So the first thing we do is that we go from kernel mode to user mode. We drop the privilege level. While entering, while making the syscall instruction, we raise the privilege level. Now while exiting, when we are executing the SRET instruction, we will drop the privilege level, right? And finally, what we'll do, we'll restore the program counter from the saved register. Remember what we did when we executed the syscall? We saved the program counter where the user process was executing in a well-known register. So now what we will do, we'll take the saved program counter and restore it so that the user process can start executing. And once the program counter changes, we are in the user process, right? So the next step is that we are in the user process, but obviously we are currently still in the library, right? So what does the library do? Remember that piece of assembly code which we executed when we were invoking the system call, where we are pushing the parameters, giving the system call number. Now in step 8, in that assembly code only, there is a logic so that the library can basically fetch the return value and the error code, right? If it is successful, then there is a return value. If there is an error, then there is an error code. So those values the kernel has placed in certain registers from where the library can take them and then return to the user application. So in the second step, we were pushing the parameters. In the 8th step, we are basically now getting the return value or the error code and returning to the user application. So the last step is that now we are in the user application, right? We have exited the library also. We are now in the application code. We are at the statement where we started, the wrapper statement. Here we were invoking the system call, right? So at this wrapper statement, we will just check the value that was returned by the system call, whether it was a success or it was a failure, right? This NB, right, the number of bytes that were read. So in the case of the read system call, if it is successful, then it returns the number of bytes that were read, right? So the return value in this case will be the number of bytes that were read. If the whole operation was a failure, then there will be a error code that also we can check. And then from here, the next statement will go on. So after this, the system call is done and we can go on to executing further, right? So this is what happens in a overall, right? So this you can see we talked about 9 different steps. So another disclaimer that this is not the list of exhaustive steps that will happen in real operating systems. The exact steps might differ, right? Although the exact steps might differ, but the overall idea remains the same, right? Similar things will happen. The exact details, implementation details might be different, but at a very high level, these are the things that happen. So let me quickly recall what we just discussed. So we start at the boot time. Okay, at the boot time, the kernel registers the entry point, the address from where the trap should start executing. Whenever there is a trap, the kernel registers the address from where it should start executing. These are the entry points into the kernel. Whenever there is a trap, the execution will be started from these entry points. Then at the beginning, we are at the user process. The system call is made. As we said, this is just a wrapper. Then it goes into the C library, where in assembly code, the C library pushes the parameters, pushes the system call number, and executes the trap instruction. As part of the trap instruction, there are certain micro steps like saving the program counter, switching from user to kernel mode, and then jumping to a well-defined location, right? So we had defined the entry point during the boot time. So from that address only, the execution will start in the kernel. And before executing the system call, the kernel has to handle the trap. First of all, it stores all of the pieces of information that are related to the user process, like the stack pointer, the general purpose registers. All of these are associated with the context in which the user process is executing. It saves that. Then the kernel determines what was the reason of the trap, whether it was a system call or a exception or a routine. And depending on the reason, it has to execute the appropriate routine. So let's just say this was a system call. Then the kernel has to use the system call number and determine the exact address where the sys underscore read routine is located. Basically, it has to use the system call number to get the address of the function call which has to be executed. So that function is executed, and as part of that execution, the parameters are verified, right? And the actual operation is performed. Here in this case, the data is read from the file. And it might also happen in that in some system calls or in some traps, the current process, the execution might be switched from current process to some other process, right? And then we start returning, right? We start returning from here. So in the step 6, we just restore the values that we have stored for the user process, the stack pointer, the general purpose registers, all of those values that we had stored, we now restore those values. Then we execute the return from trap instruction, and as part of the return from trap instruction, we drop the privilege level, and we also restore the program counter. And once the program counter is changed, we are back into the user process. So in the user process, we reach the library, right? And in the assembly code, the library unpacks the return value or the error code and returns to the user application, where the user application can handle the return value or the error code and then go on to further execution. So this was a brief review of what all we discussed. So guys, this was it for this video. We took a closer look at what happens in this one system call, right? So this system call, we enlarged and looked at it in great detail. You can see it has several different steps, right? It is not so simple as here. It has several different steps. So we tried to take a closer look at system calls, and now we are done with system calls, and from next video onwards, we'll look at a different type of trap, that is exceptions. So guys, this was it for this video. Thank you very much for watching, and I will see you in the next video. Thank you.